All right, let's continue on. So let's take a look at review of the Carnot vapor power cycle so that we can introduce the ideal Rankine cycle. So we've all been exposed to the Carnot vapor power cycle, true? That was in Thermo 1. So this is a review. So what we have is, I'm going to sketch it. You have a boiler followed by a turbine followed by a condenser, followed by I'm going to call it a pump, and then there we go. And so the fluid would flow out of the boiler and go to the turbine, out of the turbine to the condenser, out of the condenser to the pump, out of the pump to a boiler. And so it does a loop. The steam or the working fluid, typically it's water, steam goes in a loop through these four components. We introduce states. It's common to have state 1, but there's nothing special about it. You could put state 1 anywhere, but it's common to put state 1 coming out of the boiler and into the turbine, state 2, state 3, and state 4. And then often we analyze things like the heat added QB. And I put a lowercase q for it's the amount of heat added per kilogram of steam going through the boiler. How many kilojoules were added to each kilogram of steam? That is a Q dot divided by M dot. The rate at which heat is being transferred into the boiler divided by the rate at which mass the steam is flowing through the boiler. That's lowercase q. True? Likewise, the turbine produces some power, lowercase wt. Is lowercase wt the power out of the turbine divided by the mass flow rate through the turbine? Yes. What are the units on lowercase wt? Kilojoules per kilogram, right? Okay. So we'll use that notation. At this point, the condenser really is rejecting heat. So let's put Q sub C, and we know that it's going to go against our traditional sign convention of heat transfer into a system, and the system would be the condenser. But now it's going to be out of the condenser, positive out. That just makes more sense. Likewise, for the pump, you put that WP goes into the pump, not out of the pump. So it came out of the turbine. That's consistent. Power out or work out of the turbine is consistent with our sign convention. All right. If we do a first law analysis for each component, we can calculate what is the equation for Q sub B. First law analysis around that boiler, what do we find? It's going to be H1 minus H4, isn't it? It's an increase in enthalpy. We neglect changes in kinetic potential energy. It's operating steady state, and there is no work, just only heat transfer in the boiler. Likewise, for the turbine, we find that it's H1 minus H2, isn't it? First law analysis around that turbine gives us that Q or WT is H1 minus H2. How about Q of the condenser? Notice the direction. The condenser, the QC is out of the condenser. That's a positive out. It's H2 minus H3. And WP, it's an into the pump, H4 minus H3. Sorry, I'm trying to economize on space, but it's H4 minus H3. Are all of these components, the flow through each of these components, is everything internally reversible? Yeah, it's all int-rev or internally reversible. What does that mean? There's no irreversibilities in the turbine, no irreversibilities for the flow going through the boiler, through the condenser, through the pump. All right, let me ask this question. It's a Carnot vapor power cycle. State 1 is saturated vapor. That's where we pick it. We pick state 1 to be saturated vapor. Okay? That's a typical assumption. What about state 4? Saturated liquid. All right? And we neglect, there's negligible pressure drop through the boiler, so that pressure at 1 is equal to the pressure at 4. That's the high pressure. It's the high pressure. Now, there's negligible pressure drop through the condenser, so that's P2 is equal to P3. That's the low pressure. So we find, I'm just going to kind of cut the system in half here, that on that side of the line, it's all high pressure. And on that side, it's all low pressure. The pump, you have the pressure gain across the pump. Across the turbine, you have the pressure drop. True? Okay, here's the question I was going to ask. Talk to me about T4 versus T1. What is the relationship between temperature at 4 and the temperature at 1? Is it greater than, equal to, or less than? Is T4 greater than 1, equal to 1, or less than 1? Okay, we have a vote for equal. Have a vote for less than. Let me ask this again. Is the pressure at 1 equal to the pressure at 4? Is it saturated liquid at 4 and saturated vapor at 1? So what do we conclude about the temperature at 1 and the temperature at 4? They're going to be equal? What I'm going to do is I'm going to pause, and I know some people have the right answer, some don't. And so what I want to do is I want everybody to get an answer, and then I want you to even, if I come around and ask you, be able to explain why. Give me why. All right? Tell me. You're going to tell me your answer, and then you're going to tell me why. Well, I'm sorry I can't go and visit everybody, but this is one of those mind-warping questions you get in Thermo 1. So you're dumping a whole lot of heat into the working fluid. It's a boiler. You're putting heat in, putting heat in, heat in. We already talked. We said it was constant pressure. There are no irreversibilities, no friction. There's no pump to add or boost the pressure, no device to take it away. We neglect pressure loss. It's the same pressure in, the same pressure out. True? It comes in saturated liquid, goes out saturated vapor. So what's the temperature? It has to be the same. But you dumped a whole lot of heat in. How's that happen, Professor? All that heat went into vaporization, vaporizing the fluid. Okay? If you have a water, it can exist in a liquid state. It can exist in a solid state. It can also exist in a vapor state. When it's solid, it takes energy to melt it. Right? Why does it take energy, heat transfer into it, to melt it? It's doing something with those bonds between the molecules, letting them come apart, right? So the molecules aren't stuck together in a particular orientation, frozen in a solid. But if even in a liquid, they still have affinity for each other, right? You got to break that bond too to get it into the vapor. All right? So it takes energy to melt, takes energy to boil. So this temperature is precisely the same. T1 is equal to T4. Could we sketch this on a TS diagram? I'm going to pause. I want you to sketch it on a TS diagram. Temperature entropy diagram. Professor, no, you should be able to do this. You should, no excuses. Sketch this. Give me all 4 states where they're at on a TS diagram. And you can have a book open. You can follow along with the book. But at this point, really, you shouldn't be just look at the book and say, here it is. I found it in the book. No, you should come straight out of your memory. Straight out of your memory. This is it on a TS diagram, okay? All right, so it's been a while maybe since you plotted a temperature entropy diagram. Long weekend, I guess, or something else longer. What is that? A dome. What's under the dome? It's two-phase inside. Two-phase liquid vapor. What's the point at the top of the dome? Triple point or critical point? CP, critical point. What is this? All these states that are going down this side? Saturated what? Saturated vapor. On this side? Saturated liquid. Okay, let's put a line of constant pressure, the high pressure, and then another line of constant pressure, low pressure. What does that look like on a TS diagram? Hey, they didn't pay me enough money to learn that. No, come on now. So at high pressure cuts like this, it goes like that. That would be pH, high pressure. And another line of constant pressure come up like this, come across, and go up. That would be low pressure, right? Those lines of constant pressure, they call it isotherms. No, they're called isobars, lines of constant pressure, right? Okay. So now we have to put on state 1 saturated vapor at high pressure. Is that state 1? True? And state 4 is the next easiest one. Saturated liquid at the high pressure. Is that state 4? And so the fluid's going through the boiler like that. It's boiling, going from 4 to 1 as it goes through the boiler, right? But as it goes through the turbine, where's state 2? It's at low pressure. So it's somewhere on that other low pressure line. And it's internally reversible expansion through that turbine. You do a second law analysis. You conclude, what about S on the exit of the turbine versus S on the inlet to the turbine? It's equal. So S2 is equal to S1. It's directly below on a temperature entropy diagram. State 2 is directly below. True? Now, we go to the pump. I know we're going to be condensing, but you only condense so far such that the pump is just like the turbine. It's isentropic compression. So it's straight below, 3 is straight below 4, or 4 is straight above 3. Either way you want to talk about it, but okay. And so here's our familiar box. What's that box? It's a box. It's a rectangle on a TS diagram. That's how you get the Carnot. All of the heat transfer into the cycle occurs in the boiler, and it all occurs at what temperature? TH. All the heat that's rejected out of the condenser occurs at what temperature? All the heat transfer out occurs at TC. If I do the thermal efficiency for this cycle, can I calculate the thermal efficiency 1 minus TC over TH? Even if I use steam? Even if I use ammonia? Even if I use propane? Even if I use whatever refrigerant or whatever fluid I want? Steam is, water is the most common, but yes, that's true. It'll work itself out all that way to 1 minus TC over TH. Okay. So right in here, sometimes we can sketch, oh, that's QB. This is WT. This is QC. And this is WP. So the pump work, the turbine work, the boiler heat transfer, the condenser heat transfer, all can be shown on that TS diagram. So there's a lot of information you could put on a TS diagram. Now let's go to a real diagram, the real cycle, because there's not a pump that's designed that ingests two-phase mixture and maybe 20 or 30% quality and gives out perfectly saturated liquid. That's what that pump does. It doesn't exist. So what do you do for a pump? You feed it saturated liquid. So we modify the Carnot. And now we get to the ideal Rankine cycle. A lot of times we'll change it around a little bit. Maybe I'll put the boiler here. Okay? Go out of the boiler, you go to a turbine. From the turbine, you go to a condenser. From the condenser, you go to something that actually looks like a pump. Okay? So we still have QB in the boiler, still have WT out of the turbine, QC out of the condenser, and WP into the pump. All right, I should have labeled that as pump, P-U-M-P. There you go. And we still have a high pressure side and a low pressure side. Everything over here is the high pressure, pressure high. And over here is pressure low. True? Okay. Now, let's do this. Instead of, we'll still put this as state 1. Let me leave it as blue. State 1. And this is state 2, this is state 3, and this is state 4. State 1 will still be saturated vapor. But what comes out of the condenser that goes into the pump? Saturated liquid. Compare the ideal Rankine cycle with the Carnot vapor power cycle. Where was the saturated liquid state? It was state 4, not state 3. Now it's state 3. So what I want to do is for this ideal Rankine cycle, all our processes or devices are internally reversible. You still have that the pressure 1 is equal to the pressure 4 is equal to the pressure high, and the pressure at 2 is equal to the pressure at 3, which is the pressure low. You still just have two pressures, high pressure, low pressure. And you can still plot things on a temperature entropy diagram. Temperature entropy diagram. And you could, that's a bad looking dome. Come on, you can do better than that. There. And you still have a high pressure line. And you still have a low pressure line. True? Okay. What I'd like you to do, without looking at the book or your neighbor, show me where each one of these 4 states are now on this TS diagram, and I'll go around and check a few students, okay? Show me where those states are, T1, T2, T3, and T4. All right, so a lot of people, state 1 is saturated vapor at high pressure. Then you go through the turbine, it expands reversibly. So state 2 is right there, but now you come out of the condenser. You don't stop. State 3 used to be right around here, but you take it all the way. So it's saturated liquid. That's where state 3 is. Low pressure saturated liquid, right? Now what do? You put it through the pump. What comes out of the pump? Two-phase, saturated liquid, subcooled or compressed liquid? It's subcooled or compressed liquid. It comes out right there. And I've exaggerated how far 4 is above 3 on a TS diagram. But it's supposed to be straight up. Straight up. Okay? Because it's a reversible pump. S4 is equal to S3. True? It's a little bit warmer, but not much at all. Okay, so there it is on a TS diagram. Now, one of the things you can do is you can calculate things like the work of the turbine. We did that over here. Remember this equation for the work of the turbine? Let me ask you this. If I want to compare the Carnot with the ideal Rankine, so I'm just going to use the abbreviation C for Carnot and IR for ideal Rankine. And I want to compare the work of the turbine, Carnot, versus work of the turbine, ideal Rankine. But we need to make a comparison where it's apples to apples, oranges to oranges. Steam, same fluid, I'm not changing the fluid. And the pressure high is the same and the pressure low is the same. Okay? So the same fluid, and maybe it's 10 megapascal and 20 kilopascal. High pressure, 10 megapascal, low pressure, 20 kilopascal, right? We're not changing those two pressures. The pressures, when you make the comparison between the Carnot and the ideal Rankine, the same pressures, the same boiler pressure, the same condenser pressure. Got it? You tell me, is it greater, equal, less? The work of the turbine. And it shouldn't be a guessing game, right? We should know with confidence. And then guess what you do next, Professor? You go and you say, the heat rejected by the condenser, Carnot, the heat rejected by the condenser, ideal Rankine. Greater, equal, less. Then the work put into the pump in the Carnot, the work put into the pump, ideal Rankine. Greater, equal, less. Which one? Then the last one, the Q in the boiler for the Carnot. Greater, equal, less. Q boiler, ideal Rankine. Greater, equal, less. True? Then we do this. Okay? Then we'll do this. We'll say, what about the thermal efficiency of the Carnot versus the thermal efficiency of the ideal Rankine? This is the thermal efficiency is how much of the work net out divided by Q of the boiler in. The net work out of the cycle per Q of the boiler, true? And then the last one is BWR for Carnot versus BWR for ideal Rankine. Oh, BWR, what is that acronym? BWR. Back work ratio. Back work ratio. So the back work ratio is the work that the turbine or the pump consumes divided by the work that the turbine produces. What percent of the turbine output is needed to drive the pump? Right? Because the work net is the work of the turbine out minus the work of the pump. True? So there's a lot of questions here. Each one, greater, equal, less, greater, equal, less. Why don't you try and answer some of those? Can you answer any of them? And then I'll come around and take a look. All right, ready to press forward. These are non-trivial. Let me ask you, should I give you more time to work on it? Like next time replay, or should I just talk about it? Talk about it? There's one had 5 of the 6 correct, and then they went from 0 of 3 and 0 of whatever, 1 of 4 correct. Okay, so the work of the turbine out of the Carnot versus the work of the turbine out of the ideal Rankine. State 1 and state 2 are exactly the same on both of these TS diagrams. So the work of the turbine out is the same for both of them. The same pressures, saturated vapor coming in, comes out in the 2-phase. It'll have the same quality, the same entropy, same enthalpy exit. Okay, now the condenser. You're going to start at state 2, the same state 2, but you're going to have to go to state 3. Here's where you used to stop for the Carnot, but now you have a little bit more to condense for the ideal Rankine. See that? So for the ideal Rankine, you have to throw more heat out per kilogram that goes to the condenser. True? True. What about the work of the pump? Well, that pump was a very special pump in the Carnot. It really doesn't exist, but to take 2-phase and boost its pressure is going to do a whole lot of compression on that. It's going to be very expensive. It's going to be very expensive in the Carnot. All right? For a pump to do that. Okay? So the pump for the Rankine is much smaller. And that's the beauty of the Rankine. It takes a lot less energy to boost liquid water, the same pressure difference, versus vapor. Superheated vapor or saturated vapor, the same pressure boost. No. It's very expensive to boost the pressure of vapor because it's compressible. And liquid's essentially incompressible. How about the boiler? Now look at, you're used to heat it from 4 to 1. It was all just changing phase. You've got to get it up to start to get to boil before it boils, and then it boils the whole way, right? So there's more heat put into the boiler because you've got to heat it up. It was subcooled liquid. You've got to get it up to saturated liquid at that high pressure. There's a lot of heat coming in here and the same amount coming in there. So the heat transfer in the boiler is greater for the ideal Rankine. What about the thermal efficiency? Well, you would like to think they're equal, but you can't beat the Carnot. And is the ideal Rankine equal to Carnot? Let me ask this question. Is everything frictionless, internally reversible? Yes. Okay, what are other considerations for the Carnot that made it the best? Is all of the heat transfer that's brought in at temperature TH into the working fluid? And is all of the heat that's rejected out of the working fluid, is it all taken out at TC, the low temperature? Okay, what is the temperature of the liquid that goes into the boiler right there? State 4 comes right in. What is the temperature at 4 right there? What did it used to be coming in to the boiler at 4 for the Carnot? Is this temperature lower? Is there some heat transfer required to heat up the liquid water, the feed water? Do we have the same efficiency? And that's the reason why. The reason why is tucked right there. Because the feed water into the boiler is cold. And so you're bringing in heat for that part of the heat that's coming into the working fluid, into the boiler early on, is just to heat up the cold feed water, to get it up to the boiling point, and then finally change phase. So which is better? Carnot is better. Thermal efficiency. Now this one's the hard one, the back work ratio. What do you think? We had the same numerator for the back work ratio in both of them. The work of the turbine is the same, so that's the denominator, right? But we said that the pump for the Carnot was much greater. True? So what do you think? Which one has a higher back work ratio? Which one? Back work ratio's higher for the Carnot. True or false? Anybody get 6 out of 6? Really? Hey, congratulations. Good job if you got 6 out of 6. Good job. All right.